In the last video, we applied the tool of linear programming on utility maximization situation. Now we will do the other case of optimization, that is when some unfavorable variable like cost is being minimized. So let's get to this economic application. There is an insurance company that employs full and part-time employees who work 40 and 20 hours per week, 40 for the full-time workers and 20 for the part-time staff respectively. Full-time staff are paid $800 per week, whereas the part-time workers, they are paid $320 per week. 800 is being paid to the full-time workers. Definitely it's greater than $320, which is less for the part-time workers. In addition, it is company policy that the number of part-time staff should not exceed 1/3 of the number of the full-time staff. So 1/3 of the full-time staff will be permitted as the part-time staff. Now if the number of the worker hour per week required to deal with the company's work is 900, so 900 is that total number of hours that is required for work by the labor or the worker. How many workers of each type should be employed in order to complete the workload at minimum cost? So we want to know that how much of the workers, that is the part-time worker and the full-time worker, will be employed in order to complete the task, and that should be done at minimum cost. So for this we can now apply the linear programming tool, but the first thing that we do is to mathematize the given information. So X is being used for the full-time staff and Y is used for part-time staff. This is step number 1, mathematization of given information. C is equal to X as a function of X and Y. The cost basically depends upon the hiring of the full-time and the part-time workers. The wage of the full-time worker is already informed about, and it is $800 per week. And if we want to calculate the total wage bill for the firm, it would be 800 into the number of the full-time workers. So it is equal to 800x. Now the wage per part-time worker is $320, and if we want to calculate the total wage bill for the firm for hiring the part-time workers, will be equal to their per worker wage into the number of workers of the part-time nature that they are employing. So it will be equal to 320y. Now the total bill for the firm for hiring both full-time and part-time workers will be equal to the sum of the two, that is the cost of hiring full-time workers and cost of hiring the part-time workers. So this objective function is to be minimized. Now we come to the constraint side. As we are already told that the total worker hours, they are given and they are 70. So they are at least 70. Now we have to remember this, that they are at least 70. Either they are equal or they are at least 70. So it means that they can be more than 70 but not less. Now full-time workers work 40 hours and part-time workers work 20 hours. So we use the full-time workers time into the number of the workers that are working. The second constraint is about the proportion of the part-time workers. they are required to be at most 1/3 of the number of the full-time workers. So it means that they can be 1/3 of the number of the full-time workers, but not more than that. Therefore, what we will see is that the number of the part-time workers represented by y, it should be 1/3 of the full-time workers represented by x, and it should be equal or less than that. So this is the maximum number or proportion allowed of the part-time workers. Now the two constraints that are usually there and are present here as well, because workers, they cannot be negative, so they will have non-negativity constraints. That is, the third constraint will be that there will be either 0 or at least one worker. So x will be either equal to 0 or greater than 0. And the fourth constraint is the other non-negativity constraint, that is the part-time workers. They can be at extreme situation 0, or they can be at least 1. So in this way we have the non-negativity constraints as well. Now we should tabulate all of these constraints to make things more manageable. So we have the objective cost constraint, and it is mentioned here. This is the function that was given that we want to minimize. Now this is the constraint, this is the minimum level of cost, and it is subject to these constraints. That is the first constraint, total worker hours. This is the first constraint. This is the second constraint, proportion of the part-time workers. We have developed this in our last process. Here there is a correction that the first constraint is equal or greater than 900. By mistake it was written as 70 in that constraint, so it is actually 900. So fixing this mistake, that value needs to be 900. Now we have tabulated the two constraints, the general constraints relating to the total worker hours and the proportion of the part-time workers. Now we have the third constraint and we have the fourth constraint, and these are about the non-negativity of these labor. Now let's convert these inequalities in the constraints into equalities so that it becomes easier to solve them. So when we do, we can plot these in the form of graphs. Let's talk about the first constraint. It is about the total worker hours, and here, since the sign is greater than or equal to, so it means that it exists above the curve, not under the curve. So now we are using equality instead of the inequality to make it more understandable. Now we have a straight line in terms of x and y, for which we can calculate x-intercept and y-intercept, so that we could get the two intercepts, and then we could plot them as an equation in the form of a straight line on the graph. This is the x-intercept where y is equal to 0. This is the y-intercept where x is equal to. So the value of x is equal to 0 here, and the value of y is 45. Now we can, the second constraint is about the proportion of the part-time workers as compared with the full-time workers. There is inequality where there is less than sign, so it means that the possibility is below the curve or on the curve, but not above the curve. If we look at this constraint, it looks like this, where c is equal to 0, that is the intercept is equal to 0. It means that the intercept is going to start from the origin. This is simply by putting x is equal to 0, we get y is equal to 0. And then we can get these values as well when we put different values of x. That is, when we put the value of x as 1, we will get 1 over 3, because it is very simple that when we write 1 here, the remaining term will be 1 over 3. And then when we assume x is equal to 2, it becomes 2 over 3. That is the value of y. This is the value of x. When we assume that x is equal to 3, y will be equal to 1. And when x is equal to 4, y will be equal to 4 over 3. You can judge it from this equation. Now, after developing this, we can plot it on the graph as well, as you will see in the next diagram. And finally, we have two non-negativity constraints that we need some full-time workers as well as some part-time workers to bring about some output. So both x and y, they are non-negative. So the graph will appear in the first quadrant, and the other quadrants, they will not be possible. Only this, that is the first quadrant, will be possible, as both x and y, they are workers, so they will be positive in terms of their number. And the step 2 is the graphing of these constraints. We can graph the two general constraints. The non-negativity constraints are only going to guide us that we will be in the first quadrant only. Let us see the graph. Let us zoom out a little bit to be able to see the graph thoroughly. This is the overall graph in which x is on x-axis, y is on y-axis. X is the full-time workers and y is the part-time workers. Now when we plot these two lines, these were two intercepts that we got from the first constraint. So we have plotted these 2 points and we have joined these points, and it is having a shade inside, so it means that there was this sign that is greater or equal. That is, it can be on the curve or outside the curve, but not inside the curve. And then we have the other constraint that we have plotted, where we had the origin as the intercept, and it had a positive slope because it was 1 over 3x. It was the equation that it had. So we have plotted it, and it was less than or equal to, so it means that it can be below this constraint somewhere here and not anywhere else. So this is the area, that is the area below this curve, it is possible, and not the area above this curve. Whereas the other constraint guides us above the constraint. It means that this is that area which is possible. So this area which I have highlighted is possible because it is both below this curve, the second constraint, and above the first constraint. Therefore we call it the feasible region. However, the points, that is this point, however, is quantifiable. This one is not quantifiable readily. We have to use the graph values, the scale, to get its value. So here we have this concern, and for that what we can do is we can try to solve the two equations simultaneously, these two constraints. And we know that this is the second constraint, this is the first constraint. From the second constraint we can put the value of y here in the first constraint, that we have done here, and as soon as we did this, we got the value of x and we got the value of y. The value of x is this and the value of y is this. However, we can already anticipate that the number of workers cannot be 19.3 and 6.4. It has to be a complete number because human beings cannot be in such fractions. Before we go ahead, we can also do this small exercise of selection of the optimum, and when we put these values, we can see, at least mathematically, these values will give us some plausible results. So these are the points that we have. This is the first point, this is the point of intersection, and this is the point which was there on x-axis, that is this point. So these are the 3 points that we can consider. 0, 0, that is the origin value, is there just for the sake of mathematical satisfaction, that we are checking the origin, how the origin operates. And origin operates in such a way that the employment cost is 0, because neither x nor y, that is neither part-time nor full-time workers are employed. This is the point of intersection that we have found with the simultaneous solution of the 2 constraints, and it gives us the cost up to this level, and this is the third point, and in this using this point we get this much of the cost. Out of these 3, this one is illogical because they cannot be 0, x and y, they have to be positive in order to give us some level of output and hence some cost. So we only consider these 2, out of which this is the minimum level, so we choose this at this stage. However, when we come out of this mathematical process, in economic and real life situation, we see that an insurance company cannot hire this fraction of the employees. So there is a need for some recalculation or some adjustment, and that is done with the help of integer programming. And integer programming is basically the conversion of the linear programming results into integers that are meaningful, especially when it comes to human beings or workers. So in order to convert this unacceptable sort of values into acceptable values or whole numbers, we are going to experiment with some other values. That is, instead of 19.3 I can experiment a higher value of 20, and instead of 6.4 I can experiment with a lower value and with a higher value, and then I can experiment with a even higher value, that is 21, 21 and 21, and with 21 I can experiment lower value, that is 5 and 6 and 7. In this way I can experiment with certain values, and let's do this. And this is called as integer programming accordingly, and on the graph we can view it. We have taken whole numbers on x-axis as well as whole numbers on y-axis, so that it gets applicable to the workers. So this is that one point, and these are other points that we have chosen to experiment. You have seen these values that we have chosen. Now there is a feature of these points that they are satisfying the feasible region. They are within the feasible region because they are below the second constraint and above the first constraint. This is something that makes them follow the restrictions that we have of the inequalities of less than an equal and greater than an equal. So out of these we can choose one that minimizes the cost, and this is done in the next table. So here you see that the cost function is now solved by using various combinations, and these are those combinations. We have experimented with them. This combination is giving us this level of cost, and second combination, third, fourth and fifth combinations, which are integers in nature. So this first one is actually that combination in which we have the lowest possible cost as compared to the other costs. So we choose this combination, which is 20 and 5. We can also view it here. This is that point that is found to be optimum because it gives rise to the lowest cost. It is on the first constraint, and it's not below it, and it is below the constraint, the second one, and it is not above it, following these restrictions of inequalities. So this is an acceptable value, and we can choose this to find out the minimized cost. And here the interpretation is furnished that if we use this, we will get a more meaningful result as compared to these two values that were found to be critical. However, they were not meaningful from the real life and economic point of view. So integer programming was resorted instead of these fractions. We have used the integer combination, that is 20 and 5. When we use the integer programming, we get this much of the minimum cost. When we use the linear programming, it was this much. Here this minimum cost is greater as compared to the linear programming cost, which definitely is not a good thing, because we want the cost to be minimum, and here this minimum is exceeding a little bit. But the problem is that we cannot violate the number of the workers, who should be a complete number, and therefore this is the combination that can befit the situation where 20 of the full-time workers and 5 of the part-time workers should work instead of 19.3 and 6.4, which is not logically acceptable. It compromises the level of the cost by increasing it a little bit, but it was necessary because the workers cannot be in fractions. So in this way we have conducted the linear programming analysis, and in this linear programming analysis of cost minimization, we resorted to integer programming, which was a refinement to our results of linear programming when it comes to the fractions and whole number requirements of the decision variables. And this was the whole process conducted in this economic application of linear programming, where we are trying to minimize an unfavorable variable, which is employment cost. Thank you.